So I know that when we were in class, we left off talking about hemoglobin, and that hemoglobin was that 4 polypeptide protein that was found in erythrocytes, that within each of the 4 polypeptides there's a heme group, and within the center of each heme group is an iron molecule that is the iron is the compound that binds oxygen. So how do we get the iron that we need to make hemoglobin? It's ingested in our diet. When initially all iron is ingested as a mixture of iron 2+ and iron 3+. And once that mixture is in the stomach acid is going to reduce all of the iron 3+ to iron 2+. So now we have all of the iron is iron 2+. That iron 2+ is then bound to gastroferritin. Think of ferritin. Ferritin always means iron. Ferritin, ferrin, iron. The iron 2+ is going to bind to gastroferritin. Think gastrostomach, ferritin, iron. So this is the carrier molecule in the stomach that binds iron. Gastroferritin will then transport all the iron 2+ into the small intestines, where it gives up the iron to allow the iron to be absorbed into the blood. Within the blood, the iron is bound to what's called transferrin. Transferrin, think trans meaning transport. Remember ferrin meaning iron, so this is the transporting molecule for iron. Then transferrin then transports the iron throughout the body and the blood. As it's transported, much of the iron 2+ will be stored in the liver, where the transferrin will give up the iron to a molecule called apoferritin. And apoferritin, when it binds iron, will become ferrin. Or ferritin. It's binds apoferritin that then will be stored as ferritin. Apoferritin bound to iron. The remaining transferrin will continue to transport the iron to other organs, such as the red bone marrow, where iron is used to make hemoglobin, myoglobin, and anything else that iron is required for. So, just to summarize here, we ingest a mixture of iron 2+ and iron 3+. In the stomach acid reduces all of the iron 3+ to iron 2+, and the iron 2+ is then bound to gastroferritin. Gastroferritin then transports the iron out of the stomach into the small intestines. In the small intestines, the iron is released from the gastroferritin so it can be absorbed into the blood. Once the iron is in the blood, transferrin will bind to the iron and transport it in the blood. Some of the iron is stored as ferritin in the liver when the iron is bound to apoferritin. So iron plus apoferritin equals ferritin. So you bind iron to apoferritin and you have ferritin. The remaining transferrin that with the remaining iron that isn't stored in the liver is distributed to other organs where that iron can be used to make hemoglobin, myoglobin, and any other protein molecule, any other substance that requires iron in the body. So life and death of erythrocytes. We talked about how it's, Mom, can you turn that off? Sorry about that. So the life and death of erythrocytes. So we talked about iron and that we need it to make hemoglobin. And if you remember, I said that erythrocytes are really just a big bag of hemoglobin. So where do we get what we need to synthesize hemoglobin and thus erythrocytes? We get the iron from, we talked about how we get the iron, but we need other things, right? We need proteins, we need things to be able to be synthesized, and so forth. We get nutrient absorption in the small intestines, amino acids, iron like we talked about, folic acid, and vitamin B12. These nutrients are then used in erythropoiesis in the red bone marrow. Once, remember, poiesis, it meaning production, urethra meaning erythrocytes. So erythrocyte production, erythropoiesis. The erythrocytes then can circulate in the blood for up to 120 days. Expired or old erythrocytes are then broken down in the liver and the spleen. Once the erythrocytes are broken down in the liver and the spleen, any fragments outside, with the exception of the hemoglobin, will be phagocytized. Remember what phagocytosis means, meaning cells eat things up. So any of the fragments that are not hemoglobin will be taken up by cells that perform phagocytosis, like macrophages. And then the hemoglobin will be degraded separately. When we degrade the hemoglobin, we separate the globin, meaning the polypeptides, from the heme group. The polypeptides / globin will be broken down into individual amino acids. And the heme group will be broken down into biliverdin and iron. Biliverdin will then be converted into bilirubin. Bilirubin will then be converted bound to bile, and the bilirubin plus bile will become feces and be excreted. The iron will be stored, released, meaning it's bound again to transferrin, or lost by blood loss through menstruation, injury, etc. So where do most red blood cells die? The answer is C, the spleen and the liver. So now focusing on this erythrocyte production that happens in the red bone marrow. Erythrocyte production, erythropoiesis. The red blood cells can survive about 120 days, and then the spleen will remove most of the old erythrocytes from circulation. However, these erythrocytes that we lose by the spleen taking up the old ones must be replaced at a rate of 2 to 3 million cells per second. And this erythropoiesis is going to occur in the bone marrow, where pluripotent stem cells in the red bone marrow will differentiate into all of the different types of blood cells. So all of the red blood cells and white blood cells and platelets. Remember that platelets, as we talked about in lab, platelets are coming from megakaryocytes. How do we stimulate erythropoiesis? Erythropoiesis is stimulated in order to correct hypoxemia via a negative feedback loop. Hypoxemia means inadequate oxygen transport of the blood. When there's an inadequate amount of oxygen in the blood. How does this occur? So as the blood circulates throughout the body, when it arrives in the liver and the kidneys sense that there's a reduced oxygen concentration within the blood. And as a result, the kidneys will secrete erythropoietin. Erythropoietin, think of erythropoiesis. Erythropoietin is a hormone that stimulates erythropoiesis. So the kidneys will secrete erythropoietin into the blood, and erythropoietin then will circulate until it reaches the bone marrow, where it will stimulate erythropoiesis. As a result of this increased erythropoiesis in the bone marrow, we'll get increased circulating erythrocytes, and as a result, increased oxygen carrying capacity. This increased oxygen carrying capacity that's the result of this increased amounts of erythropoiesis will then remedy the fact that we've had that low oxygen carrying transport. And as a result, the kidneys will stop secreting erythropoietin because they'll recognize that the oxygen transport in the blood is sufficient. Where does this erythropoiesis occur? Hematopoiesis, what's the difference between hematopoiesis and erythropoiesis? Hematopoiesis meaning blood development, white and red blood cells. I think I made an error before. Erythropoiesis meaning just the production of erythrocytes. Hematopoiesis would be the production of both erythrocytes and leukocytes or white blood cells. That would be, if we Googled it right now, that would probably be the distinction between erythropoiesis and hematopoiesis. hematopoiesis, meaning the production of both white and red blood cells, or leukocytes and erythrocytes, is going to occur in the red bone marrow that's found within the axial skeleton and girdles, meaning the os coxae and the pectoral girdles, so the pelvic girdles and the pectoral girdles, and the epiphyses of the humerus and femur, so the ends of the femur bones and the ends of the humerus bones. Erythropoiesis, meaning the maturation of erythrocytes. Maturation of erythrocytes. The process involves when hematopoietic stem cells become hemocytoblasts. Hemocytoblasts, if anytime that you hear the word blast on the end of a cell, it means that that's a building cell. So hemocytoblasts, meaning the cells that are going to build blood cells, or will build blood cells, become blood cells. Hemocytoblasts. Blast always means a building cell. You remember from last semester, osteoblast meant a bone building cell. Hemocytoblasts, meaning the cells that are going to give rise to all of the other formed elements of the blood. Erythrocytes, leukocytes, and thrombocytes, aka platelets. During the maturation of erythrocytes, because we're specifically talking about erythrocytes here, the hemocytoblasts that will become pro-erythroblasts. They'll differentiate, so they're going to take on a specific branch of development and or specific route by becoming what are called pro-erythroblasts, meaning building cells that are specifically going to build up erythrocytes. So these are different from hemocytoblasts, because hemocytoblasts are going to give rise to any and all of the formed elements of the blood. Pro-erythroblasts, once the hemocytoblasts differentiate into pro-erythroblasts, it means that those cells that become pro-erythroblasts can no longer become all of the formed elements of the blood. They can only become erythrocytes. So pro-erythroblasts will develop into early erythroblasts, or the colony-forming units of erythrocytes. CFU, colony-forming units. Early erythrocytes are going to mature through 3 different phases. The first phase is that we will get increased ribosome synthesis. What are ribosomes used for? Ribosomes are used for protein synthesis. So the ribosomes are synthesized in excessive amounts. We get lots and lots of ribosome production. And the ribosomes will help make the polypeptide chains or globulins of hemoglobin. So the result of the increased ribosome synthesis will be that we'll get increased hemoglobin synthesis. And so as the hemoglobin accumulates, the early erythroblasts become late erythroblasts, and then become what are called normal blasts. Remember, the blast always means a cell that's building and becoming something. In phase 3, the normal blasts are going to eject the nuclei of the cell. And once the nuclei is ejected, the cells are then called reticulocytes. If you want to think about it for a second, one of the connective tissues that you learned about last semester, reticular connective tissue. Where do you find that? It's found in organs like the spleen, like the bone marrow, like the liver, like the lymph nodes, where blood circulates and is filtered. So reticulocytes are early or premature, let's not say premature, let's say immature erythrocytes. And so as the reticulocytes mature, they will become mature erythrocytes. So the erythrocytes start as hemocytoblasts that then become proerythroblasts. The proerythroblasts will become early erythroblasts and start accumulating massive amounts of ribosomes. Those ribosomes will then allow for hemoglobin accumulation. And once we have a lot of hemoglobin accumulation, the cells will become normal blasts, and the normal blasts will then eject the nuclei from the cells. And once the nuclei is ejected from the cells, the normal blasts will be called reticulocytes. And reticulocytes will continue to mature into erythrocytes. So just an idea, just to maybe clarify a little bit more here. So here's I'm just going to explain one part of this graph here. So we start with this pluripotent stem cell. And the pluripotent stem cells, if you remember, pluripotent stem cells stem cells are great because they can become any type of cell. So pluripotent stem cells will then start to differentiate into what are called myeloid stem cells and lymphoid stem cells. Once these cells become myeloid stem cells, they can become any of these types of cells right here. And we'll continue to talk about this diagram later. But one of the things that myeloid stem cells can become are the hemocytoblasts. And some of the hemocytoblasts will then differentiate to become proerythroblasts. And this is where those phases are going to occur. So we get the ribosomes being synthesized in massive amounts, and then the accumulation of hemoglobin, and then the nucleus being ejected from the cells. And once the nucleus is ejected from the cells, these cells are called the reticulocytes will continue to mature and become mature erythrocytes, red blood cells. What are the basic requirements that are needed for iron erythrocyte production? We talked about iron before, but the other components are proteins and lipids and carbohydrates, folic acid, which is also called vitamin B9, which is necessary for DNA replication in order to make the purine ring and thus allow for cell proliferation. Remember that two of the different nucleotides that make up the DNA are purines. So in order to make those two nucleotides, we need vitamin B9. And without it, we don't get the cell production to produce erythrocytes. An additional vitamin that we need is vitamin B12, which is also necessary for DNA replication and cell proliferation. Has a function similar to folic acid. So iron, proteins, lipids, and carbohydrates, folic acid, or vitamin B9, and vitamin B12. So now that we've talked about erythropoiesis, let's talk about anemia. Anemia meaning below normal oxygen carrying capacity within the blood. It is often characterized by a low hematocrit. Different types of anemia. We have nutritional anemia, usually because we do not have enough iron. Pernicious anemia, meaning the lack of B12, deficiency of B12. Aplastic anemia, renal anemia, meaning where the anemia is occurring due to the kidneys. Hemorrhagic anemia, meaning a major blood loss, we get a hemorrhage. And hemolytic anemia, meaning that the cells are being broken down within the body abnormally. So I think someone asked in the class about these, about sickle cell anemia, and how did that differ from something else? I can't remember what it was. And I said that it was different. And it is different. Oh, I think it was spherocytosis. Sickle cell anemia. Spherocytosis meaning that the erythrocytes become spherical. Sickle cell anemia meaning that they start to take on a sickle-like shape. So sickle cell anemia is an inherited disorder where the normal red blood cells sickle in shape. They look like sickles. They sickle because the hemoglobin protein has a mutation in it that when it binds oxygen, it takes on a more linear branching-like structure with the other hemoglobin within the erythrocytes. And the result is that you get these long chains of hemoglobin. And these long chains of hemoglobin are going to force the erythrocytes, because the erythrocytes are fairly flexible in shape. These long chains of hemoglobin are going to force the erythrocytes to become linear in their shape also, going from this circular disc-like shape to more linear sickle-like shape. And the result is that this red blood cells cannot move as easily through the capillaries and the smaller vessels of the blood, smaller vessels in the circulatory system. And as a result, the cells, these sickle-like sickle-like shaped cells do not get easily transported in the blood. And they start to clump together, forming clots that reduce the oxygen carrying capacity of the blood because the blood can't circulate. Once you start forming weird clots, the major problem is that first off, it's taking up blood cells that we need to move, but we also block the movement of red blood cells. And if we block their movement, we're going to block their abilities to carry and release oxygen. Polycythemia, on the other hand, so we talked about anemia meaning a low hematocrit. Polycythemia is characterized by too many red blood cells, or too many erythrocytes, which results in an elevated hematocrit. Remember, a normal hematocrit is around 45% of the total blood volume being erythrocytes. In polycythemia, the hematocrit can be around 70%. So here's some interesting questions, and I really wish that we were in class for these questions. But to keep us ahead where we need to be in class and throughout the semester, I'm just going to answer these questions here. But Sarah, a healthy 26-year-old, has a physical for her new job at Amazon. The doctor calls a few days later to report that he'd like to redo her blood tests. She gets busy at work and does not find the time to go back for another month. The doctor calls her 2 days later with her results. So she goes in, she finally finds the time in a month, and the doctor calls her with her results. Initially, her red blood cell count was on the higher end of the normal range. But now, a couple months later, 2 months later, it is more elevated and is now above the normal range. He asks her if she's experienced any life changes since her first blood draw. Sarah admits that she has started to smoke due to the stressful nature of her new job. One thing that is really scary about smoking is it increases the amount of carbon monoxide in the blood. Carbon monoxide, remember how that works. It binds 200 times stronger to the iron than oxygen does. So it essentially just blocks hemoglobin from being able to do its job permanently. Explain how this new habit of hers might result in this higher than normal red blood cell count, or this polycythemia. If you reduce the amount of oxygen within the erythrocytes and within the blood because you're dealing with some carbon monoxide poisoning, like Sarah, the result is that you have reduced oxygen transport. That is sensed in the kidneys. Remember how that's sensed in the kidneys. And as a result, the kidneys secrete erythropoietin. Erythropoietin then circulates in the blood until it gets to the red bone marrow, where it results in synthesis of more erythrocytes. So as a compensatory mechanism for her carbon monoxide poisoning, her body is trying to produce more erythrocytes, resulting in more hemoglobin production to get her oxygen carrying capacities back to where they should be. Next one. Patient comes into a clinic with a low red blood cell count, so low hematocrit. And in that same blood test, they see a high number of reticulocytes. Well, what are reticulocytes? Reticulocytes are those immature erythrocytes. After some testing, he is discovered to have a bleeding peptic ulcer, a bleeding stomach ulcer. How do these test results relate to a bleeding ulcer? A bleeding ulcer would result in hemorrhagic anemia, meaning, and then as the blood circulates throughout the body, because you are losing erythrocytes through that blood loss, your body is going to work to compensate and keep increasing erythrocyte production, erythropoiesis. However, because it can't keep up the rate of erythrocytes that are can't keep up the rate at which this patient is losing erythrocytes, and the reticulocytes and the erythrocytes aren't allowed to mature as fast as they need to be to become mature erythrocytes before they're circulating in the blood. The result is that the body gets desperate, and rather than just seeing a few immature erythrocytes, aka reticulocytes, in the blood, you're seeing a high number of reticulocytes in the blood. So next thing that we're going to talk about here is hemostasis. Hemostasis is a natural process in which blood flows and a clot forms to prevent blood loss during an injury. Think hemo meaning blood, stasis meaning stopping. So hemostasis meaning stopping blood flow, stopping blood loss. So we do not have to have too much erythropoiesis going on because of the blood loss like we saw in the last slide. So hemostasis is a natural process in which the blood flow slows and a clot forms to prevent blood loss during an injury. There's 3 steps to this. The first one is a vascular spasm. A blood vessel is cut. Injury occurs, cuts the blood vessel. And as a result, the blood vessel immediately constricts. The smooth muscle in that blood vessel, because of the stimulation of pain receptors, constricts. The pain receptors will then stimulation of the pain receptors results in this constriction. Next, injury of the smooth muscle is going to cause a release of serotonin, a vasoconstrictor. Remember, serotonin, you saw this last semester, a neurotransmitter. Serotonin from the platelets results in a long-term vasoconstriction. So we get a short, prompt, quick constriction of the blood vessel because of the stimulation by pain receptors. Next, because there's been an injury to the smooth muscle will release serotonin from platelets, which will then result in a long-term vasoconstriction. Next, we get a formation of a platelet plug. So this is the second step, platelet plug. This results because platelets get activated. When the platelets are exposed to collagen fibers of broken blood vessels, they become spiny and sticky. These spiny and sticky activated platelets will then stick to the torn vessel walls and other platelets, and allowing for a platelet plug to be formed. So as these activated spiny and sticky platelets aggregate, they also continue to degranulate. If you remember, we talked about granulocytes, meaning cells that contain granules. Well, platelets contain granules. And when they degranulate, what that means is they release the granules from their cells. And the different granules are serotonin, ADP, adenosine diphosphate, and thromboxane A, an eicosanoid. These molecules that are released further promote vasoconstriction and platelet aggregation, resulting in this positive feedback loop. You get activation of platelets, they release their serotonin and ADP and thromboxane, which, remember, serotonin promotes vasoconstriction, and ADP and thromboxane A are going to stimulate further platelet activation and degranulation. Positive feedback. The third step of hemostasis is this activation of a coagulation cascade that results in a fibrin plug or final clot. Fibrin plug or final blood clot. This coagulation pathway is one of the most complex processes in the body. I think if you remember from lab last week, I discussed this with you and told you it was the most complicated process in the body that we know of so far. It involves over 30 chemical reactions. The ultimate goal of this coagulation cascade is to convert fibrinogen to fibrin. Fibrin is a sticky fiber to which blood cells and platelets will then stick to, making a fibrin plug that forms the blood clot, or is the blood clot. So vascular spasm, platelet plug formation because of the activation of the platelets, and then the coagulation cascade that results in the blood clotting and the fibrinogen being converted into fibrin. There's, if on that last slide, talked about the fact that this coagulation cascade or reaction pathway of coagulation is the most complicated process, physiological process that we know of so far. There's at least 30 chemical reactions in it. I'm not expecting you to memorize all of this reaction. I want you to understand and remember certain parts of it. One of the first things I want you to remember is that there's two different mechanisms. There's an extrinsic mechanism and an intrinsic mechanism. The extrinsic mechanism is external to the blood. So extrinsic meaning something outside of the blood. Intrinsic mechanism meaning something that's internal to the blood, inherent to the blood. The extrinsic mechanism is going to be initiated by clotting factors or procoagulants promoting coagulation released from damaged blood vessels and perivascular tissues. Perivascular meaning, peri meaning around, vascular meaning blood vessels, so tissues surrounding the blood vessels. The intrinsic mechanism is going to use clotting factors found in the blood itself, like platelets. In most cases, both of these mechanisms are working together to achieve hemostasis. If you look here, and I think we'll see this on the next slide, we have two different mechanisms that initiate coagulation. The extrinsic method and then the intrinsic method. Both of these ultimately initiate a common mechanism. Both of them can occur simultaneously and stimulate this common mechanism. Clotting factors. So the clotting factors or procoagulants are going to reinforce the platelet plug. Remember how that was the second step of the hemostasis. they're going to reinforce the platelet plug and convert the blood in the vicinity of the vessel, injured vessel, into a non-flowing gel. Many of the clotting factors, of these clotting factors, are formed in the liver and are always present in the blood plasma as inactive precursor forms. Remember how they end in OGen, O-G-E-N, inactive precursor forms. They're always present, but they're inactive. When one clotting factor is activated, it will then activate the next clotting factor in the sequence, resulting in this reaction cascade, where each activating step depends on the previous activating step. So each factor, looking just as at the intrinsic mechanism, meaning the mechanism that occurs within the blood, each factor, the factor 12 here, is going to activate a larger number of the factor 11. And the larger number of factor 11 will activate an even larger number of the factor 9. The many factor 9 will then activate factor 8. And those factor 8 molecules that were activated will then activate factor 10. At this result, at this point in the process, this is the common coagulation pathway. So factor 8, this from factor 12 to factor 8, this is the intrinsic pathway. From factor 10 to the fibrinogen activation into fibrin, that's the common pathway. So with these clotting coagulations, or even any reaction cascade, the number of factors activation is going to be higher than the previous number of factors that were activated. So we may start with 2 factors of factor 12, and once we've gone through all of these steps, we have activated thousands of fibrin from the two factor 12 molecules. So the extrinsic mechanism and the intrinsic mechanism ultimately are going to result in the activation of fibrin from fibrinogen. This clotting cascade that results in the activation of fibrin to produce this blood clot can be triggered by either the intrinsic pathway or the extrinsic pathway. In the intrinsic pathway, remember this is within the blood, the factor 9, meaning the Hagman factor, is activated when it comes in contact with exposed collagen in the injured vessel, or a foreign surface such as a blood test tube. This is why blood starts to clot in a tube when it's pulled out of the body. So the intrinsic pathway is set off by factor 12. when it gets exposed to collagen, or when it's exposed to a foreign surface such as a glass test tube. This clotting cascade can also be triggered by the extrinsic pathway, which requires activation by tissue factors outside of the blood, like damaged perivascular tissues. Tissue thromboplastin or factor 3 is released from damaged perivascular tissues. When it's released, it with factor 7 and calcium will activate factor 10 in the common pathway. So remember, extrinsic pathway starts with factor 3 that's released from damaged tissues. The intrinsic pathway starts with factor 12, and ultimately both of these are going to activate factor 10, which is the start of the common pathway. Well, the one thing that's important is we want clots, we like clots, but we also want clots to go away. Because once the repair is done and we're back to where we should be and we're healthy and the vessel has been repaired and there's no more blood loss, we need that clot to go away so that we can maintain our transport of oxygen throughout the body. So how do we get rid of the clot? Factor 12, remember that's the Hagman factor in the intrinsic pathway, also stimulates the breakdown of the clot. It activates the formation of it and initiates the breakdown of it, or the dissolution of the clot. So the Hagman factor, factor 12, activates two different cascades. It activates a fast cascade resulting in clot formation, and a slower cascade that's going to result in plasmin activation. Plasmin, which is trapped within the clot, will ultimately dissolve the clot through breaking down the fibrin, or fibrinolysis. So Hagman factor, activated through the intrinsic pathway, initiates this quick cascade to result in the clot formation to prevent the blood loss. But at the simultaneously, the Hagman factor will also activate plasmin within the clot that will start the slow breakdown of the clot by breaking down the fibrin. Thus, another word for this dissolution of the clot is called fibrinolysis. So this second cascade, Hagman factor 12, is going to activate, in this second cascade, it's going to activate a protein called kallikrein from prekallikrein. So it activates prekallikrein to make it into kallikrein. Kallikrein will then cleave the plasminogen and forming the activated plasmin. So Hagman factor, or factor 12, to cause fibrinolysis of the clot is going to activate kallikrein, trigger the production of kallikrein, that will activate, by cleaving plasminogen, it will activate plasmin that will then break down the fibrin polymer. Platelets. So platelets, remember that another word for platelets is thrombocytes. Platelets are cell fragments that are shed from megakaryocytes. Remember megakaryocytes, mega meaning big, karyo meaning a nucleus, cyte meaning cell. So these are really big cells that have a lot of nuclei within them. These megakaryocytes are going to shed these fragments in the bone marrow. And these fragments, the platelets, lack nuclei, but they do have the organelles and the cytosolic enzymes necessary for generating energy and synthesizing secretory products. They also have large amounts of actin and myosin. Why would they want large amounts of actin and myosin? Think about what you learned about muscle last semester. They have large amounts of actin and myosin in order to allow them to contract and move and relax and change shapes. Platelets or thrombocytes can remain functional for up to 10 days, for approximately 10 days. And like the older erythrocytes, they are also removed from circulation by tissue macrophages. Thrombocytes do not leave the blood as white blood cells do. Approximately 1/3 of them will be stored in blood-filled spaces within the spleen and be released when needed by the sympathetic nervous system, induced when needed. And they are released when the sympathetic nervous system causes the spleen to contract, releasing these platelets into the blood. Thrombopoietin, remember erythropoietin meaning the hormone that produces erythrocytes, triggers erythrocyte production. Thrombopoietin meaning the hormone that causes platelet production or thrombocyte production. So thrombopoietin is the hormone that's produced by the liver that increases the number of megakaryocytes, thus increasing the amount of platelet production. Coming back to this original picture that we saw a while back, pluripotent stem cells can become lymphoid stem cells or myeloid stem cells. Once the myeloid stem cells can then become prourethroblasts or megakaryocytes, or this other type of cell that will result in four of our different leukocytes. So myeloid stem cells will become megakaryocytes. Megakaryocytes will result in platelet production. So we've talked about blood clotting, we've talked about breakdown of clots, and we've talked about platelets. So let's spend a second to talk about abnormal blood clotting. A thrombus is an abnormal intravascular clot. So a abnormal clot that's within the vessel that's attached to the vessel wall. An emboli is a clot that is freely floating in the blood. So thrombus is where it's attached to the vessel, clot that's attached to the vessel. Emboli is when it's freely floating in the blood. A thromboembolism, meaning resulting in increased clot formation, can be caused by roughened vessel surfaces that are associated with atherosclerosis. Imbalances in the clotting, anti-clotting systems. Slow moving blood, reduced blood pressure or increased viscosity of the blood. And it can be triggered by the release of thromboplastin. Remember what thromboplastin was? That was the factor 3 into the blood from large amounts of traumatized tissue. Hemophilia, on the opposite side of the spectrum, is when there is a deficiency of a factor needed in the clotting cascade, resulting in loss of clotting and therefore excessive bleeding. One really interesting and probably of my, if I can have a favorite clotting disorder, this is it. So abnormal blood clotting. Disseminated intravascular coagulation. If you think about that, disseminated, what does that mean? Disseminated meaning small, profuse, and throughout. Or profuse and separate. Intravascular meaning within the vessels, clots. So this is profuse throughout intravascular clots. Most often, from what I've heard from my mother, the retired nurse practitioner, this occurs as a result of a sepsis, throughout body infection. This is the result. This occurs because bleeding and clotting is occurring simultaneously at the same time. Where microclots throughout the body are going to deplete the clotting factors that are available. And then because there's reduced clotting factors, small bleeds are not going to be able to clot, causing someone to bleed to death. Because microclots have depleted all of the clotting factors within the blood. At this point, we've gotten through probably the harder parts of this chapter. We'll finish this out, and then I'll finish this recording, and this will be the end of, we'll finish chapter 18, and we'll start chapter 21 on Wednesday. So, we talked about blood typing in lab. Human blood groups. Blood typing, or the reason everyone has a specific blood type, is because of glycolipid antigens on the external surfaces of their erythrocytes. These antigens are unique to the individual. So glycolipids that are antigens, meaning antibody forming, glycolipids that are potentially able to have antibodies developed against them. So on everyone's red blood cells, we have glycolipids that are capable of having antibodies formed against them. These different antigens are unique to an individual, and they will be recognized as being foreign if they're transfused or introduced into another individual. When they're recognized as being foreign in an introduction into another individual, they are promoters of agglutination or clotting, and are referred to as at that point as being what are called agglutinogens. If you want to think about that, remember what ogen means, meaning that they're inactive. But once they're activated, such as when they're being recognized as being foreign in someone else's body, they're going to promote clotting of those red blood cells. The presence or absence of these different antigens is what is the basis of blood typing.